Here is the complete walkthrough of the Sizing Water Supply Piping Guide covering all slides. A water supply fixture unit, or WSFU, is a measure of the probable demand a plumbing fixture places on the water supply system. It represents estimated water demand. It does not represent actual flow rate. Fixture unit values are assigned based on three factors. First, the fixture flow rate when the fixture is in use. Second, the average amount of time water is actually flowing during a single use. And third, how frequently the fixture is used. Together, these factors allow us to estimate realistic demand on the water supply system without assuming that every fixture operates at the same time. When sizing water supply piping, we start with a few key factors. Pipe sizes are based on available water pressure, fixture demand, the type and length of piping, the height of the building, and the flow pressure required at the top floor. As a general rule, 3/4 inch pipe is considered the minimum size for several critical conditions. 3/4 inch pipe is the minimum size for the water service from the street main to the water meter. It is also the minimum size for the first section of water distribution piping inside the building. 3/4 inch pipe is the minimum size for a fixture supply or fixture branch serving a sillcock. It is also the minimum size for the fixture supply or branch pipe feeding a water heater. And finally, 3/4 inch pipe is the minimum size for the hot water supply pipe on the outlet side of the water heater. These are minimum requirements. Actual pipe sizes may need to be larger depending on demand, distance, and pressure conditions. Now let's look at minimum pipe sizes for smaller water supply piping. For 1/2 inch pipe, there are several permitted minimum uses. 1/2 inch pipe is the minimum size for concealed water supply piping. It is also the minimum size for serving 3 fixtures or fewer within the same bathroom of a house. 1/2 inch pipe may be used as a fixture branch pipe, except where individual fixtures or appliances require a larger size. For even smaller piping, 3/8 inch or 1/4 inch pipe may only be used under limited conditions. These sizes are allowed only for fixture supply piping that is not concealed within building partitions, or where the pipe length exceeds 30 inches. Again, these are minimum code allowances. Actual pipe sizes must still be verified based on demand, pressure, and distance. This visualizes the overall water supply design and components. This shows a typical one-story dwelling plumbing layout. This provides the fixture unit values for various private and public uses. First, determine the total demand. When you calculate the total cold water supply fixture unit demand, you will follow one of two paths depending on the type of water closets. If the building has water closets that are not fitted with flushometer valves, total the cold water supply fixture units for the entire building by adding the fixture unit values for each individual fixture. If the building has water closets fitted with flushometer valves, you still total the cold water supply fixture units for the entire building using the fixture unit table. But then you assign specific fixture unit values to the flushometer valves on each branch, starting with the most remote valve. Here are the assigned values. First flushometer valve is 40 water supply fixture units. Second is 30. Third is 20. Fourth is 15. Fifth and every additional valve after that is 10. And there is a hard rule here. The flushometer valve supply pipe may never be smaller than the size of the valve inlet. Also in step 1, you need hot water demand. Total the hot water supply fixture units for the building using the fixture unit table and assign that demand to the water heater. This chart shows water meter and branch pipe sizes relative to pressure and length. You will be given the developed length of piping. This is measured from the water meter to the most remote outlet if the water pressure at the meter is known. In our examples, you will be given the water pressure. This demonstrates cold water supply sizing starting from the remote outlet, this example, and 1 calculating total demand for a public restroom. This image shifts focus to hot water supply pipe sizing. This sets up the second example for determining total water demand. This example, the hot water supply fixture units for the example. Water closets do not require hot water, so they are not part of this hot water calculation. Now let's walk through how to use the water supply and water meter sizes for water supply systems table. Before you look at pipe sizes or fixture units, there is one critical first step. You must identify the correct pressure range. This table is divided into 3 pressure ranges: 30 to 45 psi, 46 to 60 psi, and over 60 psi. You always use the working water pressure, not the street pressure. Once you determine your working pressure, select the matching pressure range section of the table. Only after the correct pressure range is selected should you read the rest of the table. Now look to the left side of the table. Down the left column, you will see the size of the water meter and water service. Next to that is the corresponding size of the main and branch piping. These rows define the pipe sizes being evaluated. Across the top of the table, the columns represent the maximum allowable developed length of piping, shown in feet. As you move to the right, the allowable length increases. Inside the table, the numbers represent the maximum allowable water supply fixture unit demand for that combination of pressure, pipe size, and length. To use the table correctly, you check 3 things together. Your working pressure determines the section. Your developed length determines the column. And your total fixture unit demand must be less than or equal to the value shown. If your demand exceeds the value in the table, that pipe size is not acceptable. You must move to the next larger water service or branch size. This table defines the upper limits of the water supply system. It tells you what works, and just as importantly, what does not. Step 1 is always to determine the total demand on the water supply piping. At this step, you must first ask an important question. Are there water closets fitted with flushometer valves? A flushometer is a high-pressure, direct supply flushing device commonly used in public and commercial buildings. It does not use a tank. Instead, it delivers a large volume of water very quickly. Because of that high instantaneous demand, flushometer valves are handled differently when calculating fixture units. If the building does not have flushometer valves, you total the cold water supply fixture units by simply adding the WSFU values for each fixture. If the building does have flushometer valves, you must assign fixture unit values to each valve, starting with the most remote valve on each branch. The first flushometer valve is assigned 40 water supply fixture units. The second is 30. The third is 20. The fourth is 15. And the fifth and every additional flushometer valve is assigned 10. Remember this rule. The supply pipe to a flushometer valve may never be smaller than the size of the valve inlet. Once cold water D first determine the cold water supply fixture units, or CWSFU, for each apartment and for the common fixtures. Start by looking at one apartment only. Do not look at the whole building yet. Each apartment contains the same 4 fixtures: 1 kitchen sink, 1 water closet, 1 lavatory, and 1 bathtub. Using the water supply fixture unit table, assign a CWSFU value to each of these fixtures. Once all 4 fixtures are assigned, add them together to find the total CWSFU for one apartment. Next, move on to the common fixtures. These are fixtures that are not located inside individual apartments. In this example, the common fixtures include silcox, a laundry tray, and clothes washers. Again, use the fixture unit table to assign a CWSFU value to each common fixture. Add those values together to find the total CWSFU for the common fixtures. At the end of step 1, you should have 2 numbers: the total CWSFU for one apartment and the total CWSFU for the common fixtures. We will combine these values in the next step to determine the total building demand. Break time is 0.9s. Now let's calculate the total cold water supply fixture unit demand for the building. We already determined that each apartment contains the same 4 fixtures: 1 kitchen sink at 2 CWSFU, 1 water closet at 3, 1 lavatory at 1, and 1 bathtub at 2. When we add those together, the total for one apartment is 8 CWSFU. There are 4 identical apartments in this building, so we multiply 8 by 4. That gives us 32 CWSFU for the apartment fixtures. Next, we add the common fixtures. In this example, the common fixtures include silcox, a laundry tray, and clothes washers. Using the fixture unit table, these common fixtures total 12 CWSFU. Now we combine the two values, 32 from the apartments plus 12 from the common fixtures. That results in a total building cold water demand of 44 CWSFU. This value will be used in the next step to size the water service, water meter, and distribution pipe. Now we move on to hot water supply fixture units, or HWSFU. Up to this point, we focused on cold water demand. Hot water demand is calculated separately. Not every fixture uses hot water, so we only include fixtures that actually require hot water service. In this building, the fixtures that require hot water are the kitchen sink, the lavatory, and the bathtub. Using the water supply fixture unit table, we assign HWSFU values to each of those fixtures. For each apartment, the hot water demand adds up to 5 HWSFU. Next, we look at the common fixtures. In this example, the laundry tray and the clothes washers also require hot water. Those common fixtures contribute an additional 6 HWSFU. At the end of this step, we have the total hot water supply demand that will be assigned to the water heater. We will use this value in the next step to size the cold water supply into the water heater and the hot water piping leaving the heater. Now let's determine the total building water supply fixture units. We will start with hot water demand. Each apartment has a hot water demand of 5 HWSFU. There are 4 apartments in the building. So 5 times 4 gives us 20 HWSFU from the apartments. Next, we add the common hot water fixtures. The laundry tray and clothes washers contribute 6 HWSFU. When we combine those values, the total building hot water demand is 26 HWSFU. Now look at the cold water demand. From the previous step, the apartments contribute 32 CWSFU. The common fixtures add 12 CWSFU. Together, that gives us a total building cold water demand of 44 CWSFU. These two values serve different purposes. The hot water supply fixture units are used to size the water heater and hot water piping. The cold water supply fixture units are used to size the water service, meter, and cold water distribution piping. We will now use these values in the sizing table to select pipe sizes. Now let's look at how sizing works when flushometer valves are used. This approach applies to public buildings where water closets are typically equipped with flushometer valves instead of tanks. Because flushometer valves discharge a large volume of water very quickly, they create higher peak demand. As a result, they are assigned special water supply fixture unit values. In this example, we are sizing the women's restroom. We begin by identifying the most remote water closet on the branch. That fixture is always assigned the largest fixture unit value. The first water closet is assigned 40 CWSFU. The second is assigned 30. The third is 20. The fourth is 15. And the fifth and every additional water closet is assigned 10 CWSFU. These values are applied in order, starting at the most remote fixture and working back towards the supply. Next, we add the lavatories. Each lavatory is assigned 2 CWSFU. With 4 lavatories, that adds 8 CWSFU. When we total all of the fixtures in the women's restroom, the cold water supply fixture unit demand is 133 CWSFU. This total will be used later to size the water service, water meter, and distribution piping serving this restroom. Remember this rule. The supply pipe to a flushometer valve may never be smaller than the size of the valve inlet. Now let's apply the same flushometer method to the men's restroom. The process is exactly the same. We begin by identifying the most remote water closet on the branch. The first water closet is assigned 40 CWSFU, the second is 30, the third is 20, and the fourth is 15 CWSFU. Next, we add the urinals. Each urinal is assigned 5 CWSFU. 2 urinals, that adds 10 CWSFU. Then we add the lavatories. Each lavatory is assigned 2 CWSFU. With 2 lavatories, that adds 8 CWSFU. When we total all of the fixtures in the men's restroom, the cold water supply fixture unit demand is 119 CWSFU. This value represents the total demand that must be carried by the piping serving this restroom. Once again, remember that flushometer valves drive higher demand and must always be evaluated starting at the most proposed. Now let's look at the unisex restroom. Even though this restroom is smaller, the flushometer method still applies. We begin by identifying the water closet. Because this water closet is equipped with a flushometer valve, it is assigned 40 CWSFU. Next, we add the lavatory. The lavatory is assigned 2 CWSFU. When we add these values together, 40 plus 2, the total cold water supply fixture unit demand for the unisex restroom is 42 CWSFU. This restroom is calculated separately and then added to the men's and women's restroom totals later. Even a single flushometer valve can significantly increase demand, which is why this step is important. Where this slide belongs in your deck, order should be women's restroom, men's restroom, unisex restroom, common fixtures, total building, CWSFU summary. You didn't miss the math, you just needed the narrative bridge, and now it's complete. If you want, next we can check slide numbering for type wording, so students don't confuse urinals versus water closets, or move into the pressure calculation step. In addition to the restroom fixtures, we also need to account for common fixtures in the building. Common fixtures are fixtures that are not located inside the men's or women's restrooms, but are still connected to the water supply system. In this example, the common fixtures include a service sink, a kitchen sink, and a silcock. We assign cold water supply fixture units to these fixtures using the water supply fixture unit table. The service sink is assigned 4 CWSFU. The kitchen sink is also assigned 4 CWSFU, and the silcock is assigned 5 CWSFU. When we add these values together, the total cold water supply fixture unit demand for the common fixtures is 13 CWSFU. This value will be added to the restroom demand to determine the total building cold water demand. It is important to remember that common fixtures are counted once for the building, not once per restroom. Now let's summarize the total cold water supply fixture unit demand for the entire building. Each area of the building was calculated separately using the appropriate method. The total CWSFU demand for the women's restroom is 133. The total CWSFU demand for the men's restroom is 119. The total CWSFU demand for the unisex restroom is 42. In addition to the restrooms, the common fixtures contribute 13 CWSFU. When we add all of these values together, the total cold water supply fixture unit demand for the entire building is 307 CWSFU. This value represents the total cold water demand that the building water service, water meter, and main distribution piping must be able to support. In the next step, we will use this demand along with the working pressure and develop length to select pipe sizes from the water supply pipe and water meter sizes table. Now we determine the total hot water supply fixture unit demand for the entire building. Remember, hot water demand is calculated separately from cold water demand. Only fixtures that require hot water are included. Water closets and urinals are not included in this step. In this building, the fixtures that require hot water are lavatories, a kitchen sink, and a service sink. There are 7 lavatories, each assigned 2 HWSFU. That contributes 14 HWSFU. There is 1 kitchen sink, assigned 4 HWSFU. There is also 1 service sink, assigned 4 HWSFU. When we add these values together, 14 plus 4 plus 4, the total hot water supply fixture unit demand for the entire building is 22 HWSFU. This value is assigned directly to the water heater. It will be used to size the cold water supply into the heater and the hot water piping leaving the heater. At this point, step 1 is complete. We now have both the total CWSFU and total HWSFU needed to move into pressure and pipe sizing. Now that we know the total building demand, the next step is selecting the correct pressure range from the water supply and water meter sizes table. This step is critical. If the wrong pressure range is selected, the entire pipe sizing will be incorrect. In this example, the building has a working water pressure of 50 psi. Remember, working pressure is not the street pressure. It is the available pressure after accounting for elevation loss. Once the working pressure is known, we locate the matching pressure range in the table. A working pressure of 50 psi falls within the 46 to 60 psi pressure range. That means all sizing for this building must be done using the 46 to 60 psi section of the table. We do not reference the 30 to 45 psi section, and we do not reference the over 60 psi section. Once the correct pressure range is selected, we can move on to checking developed length and fixture unit demand. The pressure range selection always comes before pipe size selection. Now that the correct pressure range has been selected, the next step is choosing the developed length column in the table. Developed length is the total length of piping from the water meter to the most remote fixture. It is not a straight line distance. It includes all horizontal runs, vertical rises, and offsets along the piping path. In this example, the developed length for the system is 200 feet. Because of that, all sizing decisions for the building water supply must be taken from the 200-foot column in the table. We do not average between columns. We do not round down. We always size based on the actual developed length or the next higher value. With the pressure range already selected and the developed length column identified, the table is now fully constrained. From this point forward, we use the fixture unit demand to determine the required water meter and service pipe size. This sequencing matters. Pressure first, length second, demand last. Using the table lookup, we can now confirm the final sizing results. Based on a total demand of 307 cold water supply fixture units, a developed length of 200 feet, and a working pressure of 50 psi, the required water meter size is 2 inches. The water service pipe entering the building is also 2 inches. Because this pipe serves the full building demand, the water distribution main is likewise sized at 2 inches. From this point forward, pipe sizes will begin to reduce